All right, everyone, this is Adam Green again from ATA Engineering, and welcome to this webinar. I'm talking about predicting aircraft wing icing with CFD. We're joined by Peter Newman also from ATA, and really we're going to break up this presentation into two parts. I will talk a little bit about ATA and STAR, and then Peter's going to review some work he's done earlier this year on an AIAA paper for this exact topic of wing icing with CFD. So with that, we'll get started. And so just a quick intro on who ATA are. Basically, we are an engineering services group. We really do high value engineering services, and we focus on aerospace and defense, as well as spacecraft and high speed systems. We also have a few other industries, industry in mining and themed entertainment, but really our main work is in aerospace and defense and spacecraft. And we are fully employee owned, and we really are basically a smart bunch of people. We have a lot of PhDs on staff. We have a lot of professional engineers, and our place in the industry is really to tackle the high difficulty problems that other groups can't tackle. So we do work with the likes of JPL and NASA. When they need help, they ask us. So you can see we're working at the very top of the technical level of engineering problems. We have offices throughout the US, and really you can see from that map that most of them are in areas of aerospace activity. And so I'm calling today from Boston, but we have areas throughout the US covering all of these centers of aerospace and then research. And the other thing too is that we are fully employee owned, which means that all of us, everyone on the call and everyone you interact with at ATA, has a vested interest in not only making it a fun place to work, but also making it very successful for our customers to interact with us and have a successful experience. So everyone you speak with at ATA, will be vested to make sure that your results are good and everything goes well. When you look at how long we've been around, we were originally a group within SDRC years ago, but in 2000 we split from them and ATA was created. And since then, we've basically done more and more and grown in the engineering services side. But we've also grown in our relationship with Siemens. And in 2016, we achieved the partnership with Siemens at gold level, which meant we sold enough Siemens software to reach that gold status. And since then, we have just grown and grown. And now we support more and more products. And in 2023, we became a measurement and test partner for Siemens, only one of two in the country, and really the primary one at that time. So we cover a lot of the tools that Siemens sells, and we are a VAR partner with them, selling and supporting their software tools. And so what do we do internally? Well, we do design analysis and test. And historically, majority of our work has been on the test side, but as we grow and do more and more things, these other two concepts get bigger and bigger as part of our business. And so when you look at the work we do on the test side, we do a lot of aerospace work for GVT and structures and analysis of things of that nature. So you can see that was some years ago, but a glider within ATA in San Diego was being instrumented for measuring vibration through the body and the wings. And then on the software side, we are very much specialized in Simcenter, Teamcenter, and NX. And so on the Simcenter piece of that, really today's presentation is STAR-CCM Plus, but Simcenter 3D, FEMAP, Nastran, all of those are used in-house extensively at ATA. We really have a lot of depth in our support of all of those products, especially STAR-CCM Plus, where we have over 10 users in-house now, all of which are available for help and support. And we have a very effective system for support. Obviously, a lot of it can be direct support with dedicated support engineers, but also we have a hotline support for email and web-based queries for support. It all works very well. And so that's ATA. Here's our offices. I'm on the bottom right there. But really today we're going to talk about STAR-CCM Plus, and really you have to start a presentation on STAR-CCM Plus with some eye candy. So this is a nice one from Siemens, actually, of of a drone. But if we consider the subject we're talking about today, that is ice accretion on wings, then Siemens have been doing this for a fair while. And in 2022, Scott Walensky is a guy in Siemens I know well, and he did a presentation on this subject back then. So this is 4 years ago, and he used STAR as it was then, and was able to predict basically ice buildup on wings, and also the effect on the aerodynamics of that buildup. Obviously, pretty significant back then, and things have moved on since then, as you'll see when Peter presents. But nonetheless, this is the kind of thing that we're talking about today. And so when you look at the physics involved in that, there's a lot, right? There's airflow, there's multi-phase droplets for the air, there's fluid film on the wings, there's mesh morphing to predict the growth of the ice, and then there's heat and flow and heat balance in the whole process. So when you think about what CFD can do, this particular application really pushes it pretty hard. And really, this next slide is really just for a visual of, okay, when we're looking at ice buildup on wings, what do we have? We have droplets impinging on a wing. We get a thin film model, which then freezes and builds up. And so this really just highlights all of those physics that are going on. And so when you apply that to CFD, you can model it, you can create the liquid film, which then becomes solid. But as it becomes solid, the shape of the airfoil changes. And what's nice about STAR is one of its abilities to morph the mesh based on the growth in that solid. And so, really that's one of STAR's strength in its ability to do advanced meshing and automate it. And so Scott finished up his work predicting icing and scalloping on a wing, and then also compared that to a thermally controlled wing where it had some kind of heating and how it improved the situation. So that was very effective work back then. And so the next step of the kind of evolution of that then is really if Star can do all of that, and Peter will show us a lot more detail in a moment what it can do. But if you link that process with HEEDS, you could actually do a lot of work, in the industry during aircraft design. And so a lot of people don't know what HEEDS is, so a quick intro. HEEDS is a multidisciplinary design optimization tool. So using analysis in an automated way to improve product outcomes is what HEEDS is. And it really is an automation tool for using really any of your existing tools in a automated pipeline so that you can really get more value from them. And it's a Siemens product, but it will work with almost any analysis tool. So if you've got MATLAB, if you've got ANSYS, whatever you might have, HEEDS can help you drive it and even blend tools from different vendors to create loops of automation. And this is really, I'm not going to read this, but really just the graphic here shows, going from CATIA to ANSYS through a STAR-CCM plus loop, through some kind of internal tool that might be pulling out some numbers, through it into a spreadsheet to tabulate the answers. HEEDS can automate this so that maybe it's 100 runs of STAR-CCM plus and the combined model to get you an answer that is better than where you started. So it's really just that optimization, the automation and the data management that really makes it a great tool. And this kind of sums up the four Siemens call them the four pillars of what it can do: the process automation, the efficient search, distributed execution, and then just the post-processing, all of that really helps you make the most from automated workflows. And the reason why I bring this up is because Siemens also have an example where the Honda aircraft company used STAR-CCM Plus coupled to HEEDS to basically predict the performance of a thermal heating system within the wing, really to design it so that it was able to reduce ice buildup and so forth. And so I'm going to skip to the next slide now, but basically this is the internal heating conduit that was piping hot air into the wing. And really, when you look at, okay, how do we make that work? If you've got a good STAR model for ice accretion and protection, and it's repeatable, then if you look at this model here, every one of these dots is actually a STAR-CCM plus run, and the goal here is an evaluation number up here is average temperature, right? So the warmer the temperature, the better. And for some reason, these red ones were just not acceptable in terms of CAD or stress or something else. And so remember, this would have been run automatically on some kind of HPC, probably, to really look at, how automating STAR-CCM Plus with heats can tackle this kind of problem. So it's pretty advanced. The heats in the last rev now has an AI predictor model where it can run, say, 100 models of your STAR-CCM Plus model and use that data to create a neural net and then create a lot more much faster using that data to really work through the design space. But once it's come up with a better answer, it still goes back to run the full CFD model to make sure that the machine learning and the AI wasn't creating something crazy. But nonetheless, it does let you explore a design space much faster using the AI predictor. So with that, I'm going to pass the ball to Peter. Tell me when you have it, Peter.
Yeah, the screen share should be ready. And thanks for the intro, Adam.
Oh, thank you. I'm seeing your, okay,
Yeah, are we screen sharing the correct presentation now?
you are, yes, I'm the right screen. Perfect. Way you go.
Okay, awesome. Thank you so much. And I just wanted to give another shout out to Keeds. It's a software I've used on a variety of projects, both with Star and other tools. And it's really quite amazing what it can do in terms of process automation. But back to Icing. So this is a modified presentation that I gave at AIAA SciTech, looking at multi-fidelity analysis approaches to aircraft icing with STAR-CCM Plus. So without further ado, I'll cover a brief outline. We'll just go through an intro that may overlap a little bit with what Adam presented, but should give some good context and background. We'll talk about the methods and then compare the outputs of those methods to a validation case, and then review some conclusions. So first off, icing occurs when supercooled droplets strike aircraft surfaces. And there are multiple different types or regimes of icing that are possible depending on your aircraft and atmospheric conditions. So this first type of icing on the left-hand side is rime ice. It's typically rougher, opaque, and it forms when droplets freeze rapidly on impact. And it's typically more uniformly distributed, as in the picture below, because it freezes before it can flow anywhere else. In contrast, glaze icing is glossy and denser and forms when droplets do not freeze immediately on impact. And this can lead to the formation of some pretty interesting shapes and structures because the droplets have a chance to sort of run back and freeze at other points from where they first impacted. And you often see shapes like these horns depicted on the lower right. And Adam touched on this with some other visuals, but resolving glaze ice physics requires specific modeling approaches. Specifically, it's very important to capture the external flow, droplet impingement, film flow, and phase change. So these are a couple of representations of essentially the same thing, looking at three-dimensional and two-dimensional water film mass transport. And I guess the highlight here is that we have this aircraft surface in black, an solid ice layer in gray, and the water film here in blue. And we really care about both the droplet impingement onto this fluid film, as well as any evaporation or convective transport out of the film. And we also have flow in from preceding elements and flow out to elements downstream. And then we have phase change and melting and solidification between this fluid film and ice layer. So a wide spectrum of icing analysis methods exist to tackle these challenges. They have varying applications, accuracy, complexity, and computational cost. Some useful ways to categorize these icing tools are in terms of spatial and temporal fidelity. Spatial fidelity is very straightforward, just whether or not you're looking at one-dimensional, two-dimensional, or three-dimensional geometries. And temporal fidelity refers to how often the flow field is coupled to ice growth. So single shot methods are going to couple your steady flow field with only the clean geometry and will not couple to any ice growth. Multi-shot methods will periodically couple the steady flow field to account for ice growth as it changes the shape of your aerodynamic surfaces. And fully coupled methods are going to continuously couple an unsteady flow field to the ice growth. And this table covers a few of the different methods that we'll be looking at today, sort of starting at the top from the lowest fidelity going down to the highest fidelity. So the first method we'll look at is a one-dimensional rime ice scaling method. It's one-dimensional, single shot, and solves, and the setup is very, very quick. But its outputs are very limited. It's just going to output a rime ice thickness at stagnation. And while limited, this is still useful for things like early conceptual design and understanding how potential ice growth might scale with geometry and atmospheric conditions. Moving up a step, we look at LUICE, which is a two-dimensional legacy icing code from NASA. And it's a multi-shot method that takes typically on the order of seconds to minutes to solve, and it can output two-dimensional glaze ice shapes along an airfoil. So this is useful for airfoil icing analysis, capturing more than just a single point or predictive ice thickness, and it's still more appropriate typically for the conceptual design stage rather than a full aircraft icing analysis. And as we go one step further, LUICE 3D is actually a significantly different tool from LUICE. It's more of a post-processor for CFD. So the input will be a CFD solution, and then it runs Monte Carlo droplet trajectories in order to predict the collection efficiency on our icing surfaces, and then can run and calculate three-dimensional rime ice shapes as well as two-dimensional glaze ice shapes along selected profiles. This certainly takes a bit longer to solve, typically on the order of hours to days, but it is more appropriate for full aircraft icing analysis and more complex flows than any of the prior methods. And lastly, but not least, STAR-CCM Plus. This is typically run in a three-dimensional capacity and can be run at all three temporal fidelities. Typical solve times range on the order of hours to weeks, depending on the size of your mesh and the temporal fidelity that you're running at. And we get significantly more in terms of outputs. We get fully three-dimensional glaze ice shapes, as well as the associated aerodynamic impacts of that ice growth. So this is applicable to our full aircraft icing analyses, including things like efficiency, control, and safety applications. So with that, I'll jump into a little bit more about how STAR specifically utilizes different physics regimes to model ice accretion. And it sort of uses this cycle depicted on the screen, where the first step is solving the external flow field. The second step is to compute droplet trajectories and impingement on the icing surfaces of interest. Third, it will calculate runback and solidification of the fluid film that develops. And lastly, it will morph the mesh to account for ice growth. And this would be considered one icing iteration. And the frequency of this iteration in STAR is what determines the temporal fidelity. So if we just run this iteration once for the entire icing duration of interest, that would be a single shot method. If we're running this cycle once every 30 seconds of ice growth, that's going to be multi-shot. And then fully coupled, we'll be running this iteration at each time step of an unsteady flow solution. So now I'll introduce the experimental test case that we are using to sort of compare and validate the results of these different tools. So this is an icing research tunnel test case that we used as a reference. The wing is depicted on the diagram on the left-hand side, and the different cuts highlighted in blue, cuts A, B, and C, are the different locations at which we will be comparing iced profiles. The test conditions are given in the table on the top right. And this specific test case and these test conditions were chosen for a couple reasons. First, the temperature and liquid water content of these experiments resulted in some pretty complex ice shapes, as shown in the pictures below. We have these sort of complex and finely scalloped structures that develop, which is going to be a challenge for our analysis tools across all levels of fidelity. And second, it's a relatively short ice accretion time on the order of 2 minutes, which makes it much less cumbersome and or computationally prohibitive to run the highest level of fidelity on these icing cases. So I'll comment a little bit on the measured ice shapes and how they vary depending on the location that they're measured at, because I think there's some interesting behavior here. So section A is the closest to the tip of the wing, and it showcases relatively symmetric horn growth. Section B is measured close to the midspan, and it shows asymmetric horn growth with a larger horn up towards the top surface of the wing, and then also a larger iced extent following down the lower surface of the wing. Section C is a little bit different in that it doesn't display any of these, sort of distinct horn shapes. It's a more uniform thickness across the airfoil surface, although the extent is again biased towards the lower surface. And I'll note that all of these airfoils are presented in the airfoil coordinate system, where X is the axial direction of the airfoil, and V infinity on the left-hand side indicates how the free stream direction varies with respect to the geometric twist of the wing. So section C at the root is at about 4 degrees local angle of attack, and we can see section A closer to the tip is at almost 0 due to the twist of the wing. And this is also what causes some of those symmetric growths versus asymmetric growths at different locations. And before we jump into the actual ice profiles, I'll comment a little bit on the computational timescales associated with each result. So the one-dimensional rime ice scaling is a very, very fast and sort of rough calculation. LuIce takes a little bit more time to set up, but is still a very quick computational process, taking on the order of seconds. LuIce 3D is the first method that really requires a significant chunk of time and computational expense. This took about 9 hours of wall clock time to run on varying resources due to the different steps involved between running the steady CFD solution, exporting to inputs appropriate for LuIce 3D, and then actually running LuIce 3D. But those 9 hours consumed about 320 CPU hours. And CPU hours is simply just the wall clock time multiplied by the number of processors used for an analysis. And it's a good estimate of the overall computational expense associated with an analysis or result. From there, the STAR-CCM plus single shot method took just under 5 hours of wall clock time on 64 processors, which yields about 300 hours of CPU time. The STAR-CCM plus multi-shot method took about 4 times as long, just under 20 hours of wall clock time, and just under 1,200 hours of CPU time. And the highest fidelity STAR method, the fully coupled run, took just under 4.5 days to run on 64 processors for a total of just over 6,500 CPU hours. So these are definitely taking more time to solve and significantly more resources as we step up into higher fidelity methods. So with that, we'll take a closer look at the predicted ice profiles for section A. Here we're starting with just the clean airfoil and the experimental ice shape. And this first dot is the one-dimensional rime scaling result. Now I'll comment for all the rime results that you will see here. We do expect it to be an overprediction and conservative for when rime results or when rime analyses are used to predict in glaze icing conditions. Because in glaze icing conditions, typically you have droplets running back from stagnation and away from that point, whereas with rime results, they're going to all freeze at the point of impact. So we would expect to have a higher thickness at stagnation and a more uniform distribution for all rime results, but it's still an interesting comparison. Second, we have the LUICE results, and the LUICE results for this case get the total magnitude of ice predicted decently well, but the overall qualitative shape doesn't match quite well. It's certainly a bit squashed and stretched in the axial and normal directions compared to what we actually see. And the LUICE 3D RIME results capture the ice thickness around the horns pretty accurately. But again, this is a RIME result, and we see an overprediction of the ice thickness at stagnation, which is what we would expect. And importantly, it is on the same order of magnitude and roughly close to the one-dimensional RIME scaling result that we developed earlier. Now we jump into the STAR-CCM Plus results. We see that the single-shot STAR-CCM Plus result captures the sort of flat front of this ice profile decently well, but it doesn't capture a lot of the finer details, and it also predicts iced extents that go much further back along the airfoil than the experimental measurements. As we jump to multi-shot, we start to capture some more of the details in that ice shape, and the iced extents also follow along with the experiments a bit more closely. And when we jump to fully coupled, we match the iced extents much more accurately, and we also capture this sort of flat front and horns and sort of scalloped shape of the actual iced profile. So in this case, the STAR-CCM Plus result definitely captures the qualitatively most accurate ice profile out of these methods. So as we move to section B, we see a pretty distinctly different ice shape, again, with a prominent horn towards the upper edge or upper side of the airfoil. Our one-dimensional RIME scaling result, as mentioned, is a significant overprediction, which is what we would expect. LUICE, in this case, does a very good job predicting both the total amount of ice accreted at this section and the qualitative shape. And then we see that our LUICE 3D RIME result, again, is much more uniform and over-predictive because it is a RIME result trying to predict something for a glaze icing condition. But again, it matches decently well with our one-dimensional RIME scaling analysis. Our STAR-CCM Plus single shot for section B, again, captures the flat front of the section decently well, but misses the horn at the top. And again, over-predicts our iced extents, especially on the top surface of the wing. As we move to multi-shot, we start to capture some of the finer details, and the iced extents are more accurately predicted, but we're still missing that horn at the top. And when we move to the fully coupled STAR-CCM Plus run, we do start to capture that horn at the top. And the iced extents are also more accurate, but we are sort of under predicting that horn, even though we are capturing it in some form. Now, lastly, section C, we have a slightly more uniform and rounded ice shape. Again, our one-dimensional RIME scaling is over-predictive of the glaze icing results, as we would expect. LUICE, again, is consistently capturing roughly the right amount of ice accreted, but is predicting a horn in this case where there is not one found in the experiments. So it's not capturing the qualitative shape of the ice very well. Our LUICE 3D RIME results, again, are over-predictive and very uniform, although in this case that matches pretty well with what we find in experiments, at least in terms of the shape, not the size. And again, matches pretty well with our one-dimensional RIME scaling results. The STAR-CCM Plus single shot captures the qualitative shape decently well, although again, and we're consistently sort of over-predicting the iced extent on the top of the wing. As we move to the STAR-CCM Plus multi-shot result, the overall shape is relatively well preserved, but we are predicting a slightly better we're capturing that iced extent on the top surface slightly better. In this case, the STAR-CCM Plus fully coupled does a good job predicting the overall total accreted ice, but we do predict a horn on the top surface where there is not one found in experiments. So a slight qualitative mismatch here compared to the lower temporal fidelity STAR-CCM Plus results. So all of those comparisons were pretty much qualitative. I'll jump into some quantitative comparisons here. This is comparing the ice cross-sectional area against the experiment by method. And I've highlighted the two methods that on average get the closest. So Ice actually does a really good job capturing the ice cross-sectional area. On average was within about 15% plus or minus the experimental ice profile. But again, not always capturing the qualitative shape completely correctly. And then as far as our higher fidelity results, the STAR-CCM plus multi-shot method was actually the closest in terms of the overall ice cross-sectional area to experiments, although in some cases is not always capturing all of the full details of the complicated coupling between the ice growth and the flow field. Lastly, I wanted to highlight what we get out of the STAR-CCM plus fully coupled model because it is the highest computational expense, but it allows us to get things like aerodynamic performance throughout the icing duration. So these are the drag and lift monitors throughout the entire simulation. With physical time on the x-axis, you'll notice it only goes from 0 to 12. In this case, the physical time is representative of the icing time divided by 10, because we're using a solid step time factor of 10 to sort of accelerate our icing results. So this is still representative. The ice growth through this time scale is representative of what you would get over 120 seconds or 2 minutes of ice growth. And we can see that the drag increases as we accumulate ice and the lift decreases. And these sort of discontinuities or jitters that you see in these monitors are related to when an automated remesh occurs in the simulation. Sometimes as we morph the mesh and get these complicated structures, we will create a negative volume cell or something that causes the mesh to have a problem. And in that case, we have an automated process in STAR that triggers a remesh to solve that issue without any human interaction. And I'll also note that to get good results with this method, you typically need a low Y plus mesh that requires relatively high cell counts. This is a relatively simple model of just a standalone wing in a wind tunnel. And we start with about 17 million cells. And as we remesh and accumulate ice, we get close to, or actually above 20 million cells in the entire mesh. And I'll also note that the fully coupled STAR-CCM plus sim captures some of that really complicated span-wise scalloping we see in the experimental results, as highlighted by the contours and sort of span-wise view. It doesn't capture the full extent and details of the scalloping, but with increased mesh resolution, you may be able to capture those details, although at the expense of significantly increased computational expense. So with that, we see that the high fidelity methods are generally more accurate and useful, but at the cost of increased complexity and computational expense. Our 1D rime icing method is rapid, simple, and can easily develop worst case thicknesses and evaluate how things might scale. Ice was fast and developed reasonably accurate two-dimensional glaze ice profiles, particularly good for estimating the ice cross-sectional area or ice mass, less so for the exact qualitative ice shapes. Ice 3D has a moderate computational cost associated with it and is good at conservative three-dimensional rime icing estimates. STAR-CCM plus single shot turned out to be reasonably accurate three-dimensional glaze icing estimates with moderate computational cost, typically on the order of hours. Multi-shot methods were more accurate and started to capture some of the important coupling effects associated with icing, with moderate but increased computational costs, typically on the order of a day. And the fully coupled STAR-CCM plus runs developed the most qualitatively accurate icing profiles and captured the complex coupling between the flow field, ice growth, and fluid film but requires significantly higher computational costs and can take on the order of days to weeks to run on high-performance computing resources. So with that, I'm happy to take any questions that you might have. Thank you.
Excellent, Peter. That was great. Thank you. Well, I have a number of questions that I jotted down as we were going through that, and they really come into two areas. One is the physical testing versus the experimental. Can you go back to one of those slides?
Yes.
Yeah.
It's like
So
a
so
results
so for
slide.
that one, does section C have a fuselage of any kind or not?
Section C does not have a fuselage associated with it. So in the actual experiment that this was taken from, the wing is actually extended beyond what is considered the root. And that's just a practical adjustment because they needed to elevate the wing further to get it into the section of the tunnel that they could actually develop a uniform cloud of droplets for icing conditions.
All right, gotcha. So look at this slide again then. In fact, can you look at the next section out?
Yes,
I
section
guess it
B.
doesn't matter, but just section B. So you've got this scalloping, and and if you take a 2D slice like you have and look at that answer, is it that star fully coupled wasn't as accurate because you could just be unlucky where you hit the section versus the scalloping? What do you think if you took an average distance, did a 10 centimeter slice, a 3D section, and then looked at those volumes? Do you think it would be any different because of the variation in the scalloping?
That's a good question. I think you would, because there is some like stochastic, random nature of how these like scallops develop, and we get this sort of like span-wise variation. So it would be interesting to, yeah, take like a section of the span and potentially average, or even just,
Yeah,
take slightly offset samples to understand what that sensitivity looks like.
or
But then
try and
again,
cover three scallops or something, or whatever might be the right number.
exactly.
Yeah,
But also, that behavior is seen in the experiments too. So there's some potential that, if the researchers took a slice at a slightly different section, they might also see significantly, or slightly varied ice profiles. So it would be really interesting to, to truly get a one-to-one, you might need to capture the experimental data in a different way that accounts for that span-wise variation as well.
right.
So then you might be able to compare, like two spatially averaged span-wise profiles, at these, rough local sections,
Yeah,
to get a true
gotcha.
one-to-one. But yes.
Okay, and then the other questions I have are really going back to, well, how can somebody use this, firstly in anger in a real project, and secondly, if they did want to do a HEEDS project like that one that Honda did that I showed, it feels like if you really want to do the fully coupled model, if it's going to take you 100 hours to do 1 point, then doing 100 points is kind of a non-starter. And so the first question is, if you wanted to speed this up, can you throw cores at it? If you can, you did 64, but if you did 1,000, would you get a linear speed up, or is it limited by the transient nature of it?
It is a bit limited by the transient nature of it, because the mesh in this case is only about 17 to 20 million cells. So 1,000 cores would definitely be overkill, and you would start to get into the regime of nonlinear speed up.
All right, yeah.
But 64 cores is certainly not, you know, you can throw a lot more cores at it than just the 64 to get your results
And
faster.
still get some speed up. Yeah, gotcha.
Yeah,
I
I
mean,
would estimate I off the back of my head, like, or top of my head, rather, you could pretty easily throw, 250, 300 cores at this and still be in, a mostly linear speed up regime
right.
and can run this a lot faster.
And when you look at this legend on here, the bottom two, or the bottom three star ones, you've got the single shot, the multi shot, and the fully coupled. Um, when you look at the bottom two, the difference between multi shot and fully coupled is you take some discrete time steps and then couple it and then kind of keep it static for another finite number of steps. And so, is it did you tweak what the right number of iterations where you update it should be? And can you tune that even more to get you a really good result for the kind of an optimal time?
Yeah, so there is actually a time step selection routine that LuIce 2D actually uses to dictate how long of a step it takes in between, sort of its multi-shot stages.
Ah,
And
okay.
so
Yeah.
I would actually use that to inform the time step selection for the multi-shot method. And that seems like it would be a pretty reasonable approach for a variety of multi-shot icing applications because it's sort of designed to, estimate how quickly ice might grow and how quickly or how often you might need to rerun your flow field to account for, the changes in the flow field due to ice accretion. So I don't think I have that equation in my backup slides. But yeah, there is an equation associated. If you open up the LuIce manual and look at the auto stepping methodology, there is a guideline for that I applied for the multi-shot method.
Excellent. All right. That's great. Thank you for all of that info. That's really good. And so everyone in the audience, that's answered all my questions. I apologize if I got to go first, but is there anyone in the audience who'd like to ask any questions? If you want to be unmuted or you want to type anything to the chat, please do. All right. So I don't see anybody typing. So, oh, hang on. Oh, thank you, Ray. Good presentation. Appreciate that. So everybody, the last chance, going once. All right. Thank you so much for joining us this afternoon. This webinar will be going up on our YouTube channel probably in about a week. So if you wanted to revisit this, you could. We appreciate you attending. Have a good afternoon, everybody. Bye-bye.